So here we have a car. You know what, I'm just going to start from scratch here. Inclined planes. So suppose I've got, here's a horizontal line like this, but I've got an inclined plane. So here's my inclined plane, and I'm going to make this theta. This is my angle of incline. So I've tilted this plane up by an angle of theta. And here's my little car that I demonstrated. And we can tell right away that it's going to accelerate down the incline, right? Here's the direction of the acceleration. Looks like that. Now what I'm going to do here is show you what to do with the procedure so that you can understand, use the procedure for force so that you can figure out what this acceleration is and what its relationship is to that angle of incline. Well, so let's do this. Let's draw a free body diagram of this car. And actually, I normally don't like to do this, but let's just draw the free body diagram on the picture itself. I usually don't like to do that, but in this case I'm going to. So what's the direction of gravity? Gravity is always straight down towards the center of the earth. Like that. So there's mg. The weight of the car is pulling it down. Now, because this has wheels, let's pretend that there's really no friction at all in this problem. So the plane, here's the plane, can only apply a force to the car that's perpendicular to the plane. So what do we call the perpendicular force of the plane on the car? What do we call that? The normal force, right? So the normal force, and the reason it's called the normal force is because it's perpendicular. Now here's what we're going to do. When you have a situation like this, I think you can see by looking at this picture, do you see that this normal force does no longer cancels out the weight? Right? It doesn't cancel out the weight anymore. There is some leftover weight. Now, what I'm going to do here, this is my free body diagram. It shows the two forces acting on it. It's not really a free body diagram because I've included the plane in the picture. But here's what I'm going to do. When you get a free body diagram like this, when you go on to step 3, make your x-axis parallel to the incline. And here's your y-axis perpendicular. So here's my x direction and here's my y direction. It's totally legal to do that. Now, step 3 also says now, once you've selected your x and y axis, and I've tilted it to match the inclined plane, now I have to break up all the forces into their x and y components. Pay attention right now. If you phased out, phase back in. Okay? Because if you can get this, it's going to be a lot easier. Look at my normal force. What direction is my normal force in? It's in my new y direction. So I don't need to break it up into components. It's all in the y direction. But now look at the weight. Straight down, but now y is not straight down anymore. So I'm going to break it up into its x and y component. I'm going to say here's the y component of the weight. See? It's really in the negative y direction, isn't it? And here's the x component of the weight. Now here's what I want you to see. And it's hard to do just on camera on a picture like this. But if this is the angle of incline right here, then the angle of incline in this triangle with the weight being the hypotenuse is up here. And I think you can see that if the angle of incline was 0, my weight would be straight down. Or, I'm sorry, the normal component of the weight would be straight down. But if I tilt this by theta, I think you can see that if I rotate this up by theta, this gets rotated up by the same angle. So this angle and this angle are the same. So here's my weight. Here's the component of the weight in the y direction. That's mg. Now what's going to be mg what? Here's my angle. This is the adjacent leg. So this is going to be mg cosine theta. Because it's the adjacent leg of this right triangle. Here's mg. mg is my hypotenuse. So this is mg cosine theta. So what's this going to be? From here over to here, the component of the weight that's trying to pull it down the incline. Mg sine theta. Why? Because mg is the hypotenuse. This is the opposite leg. You multiply the hypotenuse by the sine of the angle to get the opposite leg. Are you with me? Okay, I got 3 minutes. If I sum the forces in the x direction, that's going to be equal to ma in the x direction. Well, let's look in the x direction. There's only one force in the x direction in this free body diagram, and that is this. Mg sine theta. That's the only force in the x direction, where theta is my angle of incline, which is here and here. But that's equal to ma. Well, what cancels out? What's on both sides? The mass of the car doesn't matter. And so now I can solve for the acceleration. The acceleration is equal to the acceleration of gravity times the sine of the angle of incline. Well, what's the acceleration of gravity here on Earth? All your lives you've been coasting down hills on bicycles or skateboards or whatever. The acceleration that you go down a hill, if you neglect friction, is equal to 9.8 meters per second squared times the sine of the angle of the hill that you're on. Now, what if the hill has a zero angle? It's flat. What is the sine of zero? The sine of zero is zero, so you have no acceleration. What if the hill is straight up and down? Well, okay, it's a cliff. The angle of incline is 90 degrees. What's the sine of 90 degrees? 1. So it's 9.8 meters per second squared. But what if you're at a 30-degree angle? What if theta here was 30 degrees? What's the sine of 30 degrees? 1/2. What's 1/2 of 9.8 meters per second squared? 4.9. So if you're on a 30-degree hill, by the way, that's a really steep hill, a 30-degree slope, you're going to accelerate at 4.9 meters per second squared.